Hello everyone and welcome to this lecture. In the last lecture we have seen that graphs may be different but they can have same set of eigenvalues. It can be with respect to adjacency matrix, sometimes we have seen with respect to Laplacian matrix, sometimes signless Laplacian matrix, and towards end we have seen that Siddle matrix also, right? And there can be many more other matrices. So graphs may be non-isomorphic but they can have same set of eigenvalues with respect to different types of matrix associated with graphs. Okay, today in this lecture we will see a very nice technique to generate co-spectral graphs with respect to adjacency matrix. Okay, well, this technique does not guarantee that the graphs, the output graphs will be necessarily isomorphic or non-isomorphic, but yeah, it will definitely give co-spectral graphs. And then in order to prove that, we have to do basically to prove, take any other technique to prove that these graphs are non-isomorphic. Okay, so it is not guaranteed that they will always give non-isomorphic graphs. Okay, very good. So let us start with this. So for this we call actually famously Godsil, because of these two scientists, Godsil and McKay. So they have given this technique, and in short form we call it GM switching. Okay, GM switching. Okay, very good. So what is this? For this switching, actually the graph has to be in certain shape. Okay, so let me first write down, draw some shape, and then actually simultaneously I will write down, and then it will be clear what we mean by the, what is required from these shapes. Okay, so suppose your vertex set of graph is partitioned in few groups. So suppose this is group 1, and these all assume that these are disjoint subset of vertex set, and this is suppose x, and then there is one special subset that we call y. Okay, now what do you do? Okay, so let me now write the simultaneous condition also. Okay, so let G be a graph with vertex partition, and let me call with vertex partition, with vertex partition as x1, x2 up to xk, and then there is some special part that we call y, such that two conditions are actually holding, such that, okay, for any I comma j which belongs to this 1, 2 up to k, okay, any vertex in any xi, okay, will have for any xi and any vertex which, okay, and v belongs to any, so any v, so rather any v belongs to it, will have the same number of neighbors in xj, in any xj. Okay, so that means this, suppose this is the guy, okay, suppose this is the guy which have, suppose one neighbor here, two neighbor with inside it, and three neighbors suppose here, right? So another vertex in this, well, suppose this is v, so you will also have the same thing. So there will be two neighbors here, one neighbor here, and three neighbors here. Okay, so this is one condition. Another condition is this. Another condition is any vertex in y, any vertex v in y will be connected, or will have will have either sorry about the spelling mistakes, either 0 or mod xi by 2 or mod xi neighbors in any xi, in any xi rather. Okay, so any xi, okay, okay, any xi where I is from 1 to k. Very good. So that means this. That means this, if you pick any vertex here, okay, so either it is all the vertices in any given xi are neighbors of it, or half of the vertices are neighbor of it, or none of the vertices is neighbor of. So suppose this is the condition here, so suppose this may be neighbors with, also suppose these are the vertices here half, okay, suppose these are half, so this could be neighbors of, okay, and with others, so maybe I will delete this edge, okay, so half, okay. Very good. Now GM switching is this. GM switching. GM GM switching. GM switching it says. Whenever any V belongs to is having xi by 2 neighbors, okay, to any xi, okay, delete those neighbors, delete those neighbors, okay, neighbors, and make the rest of the vertices in xi the neighbors of V. Okay, so very simple one. Okay, so let us see. So for example, here switching means this. After switching, what will happen? So let me put this red one. Okay, so these will be cancelled out, and the new neighbors will be this from here. So these will be new neighbors, basically this. Suppose these are the half one. So these are new neighbors. Okay, these are killed. White ones are killed. Okay, these are new neighbors. Okay, and whenever there are zeros, you do nothing. No need to do nothing. Whenever vertices have neighbor, all the vertices of any xi are neighbor of V, then again you need to not to do anything. Okay, so the resulting graph is called what we call the resulting graph is. Okay, so the resulting graph is graph. Suppose we call G dash. Okay, G tilde is cospectral with G. We will prove that these two guys have the same eigenvalues. Okay, very beautiful. So let me go through again. So there are set different subset of vertices, and these are two conditions. Okay, and we will see that after switching, GM switching, the eigenvalues of the adjacency matrix are preserved. Okay, so let us prove it. Okay, now remember that how can we prove that two graphs have the same set of eigenvalues with respect to adjacency matrix, or for that matter any kind of matrix? Suppose that if I can show that there exists some orthogonal matrix, okay, suppose Q here, okay, and if I multiply this orthogonal matrix by A, and then suppose the inverse or transpose orthogonal, so transpose is enough, okay, such that the resulting matrix is also a 0-1 matrix, basically a symmetric matrix, and more specifically it's a matrix of some graph. Okay, it's matrix of adjacency matrix of some graph, the resulting matrix. Then we will see that these two graphs will have the same eigenvalues, right? So this we will try to find such Q for our purpose to prove that G and G dash have the same eigenvalues. So maybe we can call it A dash, right? But how to find that Q? Okay, we have seen this multiple of times, right? If we can find such a Q, then both of these matrices or then graphs will have the same eigenvalues. Okay, but how can we find? Okay, so let us start a hunt of finding such a Q. Okay, so let's suppose okay, so let us go to the proof of it. Okay, so suppose your Q, there is an orthogonal matrix. Okay, we will prove that this Q, and the way I am defining here, suppose this is equal to 2 by M, this is all one matrix, okay, times identity matrix. Okay, we will prove that this matrix is actually first of all orthogonal. So QM transpose Qm is indeed equal to Im. Second is, we will prove that if you take any matrix here, suppose this Q transpose X, or maybe just suppose Xm is any matrix, or more precisely, let me write here. Suppose X m cross n is a matrix with constant row sum and constant column sum, okay, sum, then actually the operation, if you multiply Qm, then this Xm cross n, okay, and then this Qn, okay, this is nothing but, this does not change anything, this does not change anything here, okay, very good, okay. And the last result is, if X is a vector, maybe a vector having 2m entries, where m entries are r1 and rest of the entries, and the rest of the entries are 0, okay, then this Qm, basically now because X is having 2, and let me write Q to m times, if you do this operation, then this is nothing but, basically it will, whenever there were ones, now it will convert it to 0, and whenever there were 0, this will convert to 1, okay. So this will be this operation, okay. Let us prove this fact, and after that our job is very, very simple to prove that G and G dash will, G tilde will have the same eigenvalues, okay. Proof, very good. The first proof is very, very obvious. The first one is what? This, what will be Qm transpose times Qm, right? We have to prove that this is equal to identity matrix, okay. This is, if you see that, because this is a symmetric matrix, right, because this will be a symmetric matrix, so this is nothing but, I can write this 2m jm minus im, again the same thing, right, 2m jm minus im, okay. So this is 4 by m square, and this is jm times jm, so there are m, so m into jm, okay. So maybe I will do it smaller x, because so this is multiply, okay, maybe just I will write in that simpler way. So this is mjm, okay, this is mjm, okay, very good. The next thing is 2 by m jm, then what, 2 by m, yeah, okay, yeah, again jm, yeah, very good, and then plus im. Now it is clear that you can cancel with this, so it is actually 4, yeah, this is correct. So these guys will go to 0, and so this is 0 matter, so this is im. Very good, very good. Another thing is what, so if you are having some matrix X, okay, which constant row sum and constant column, suppose the sum of these entries is, so suppose sum is, suppose C here, and suppose you take here sum is sum of is D here. Now remember that this is m cross n matrix, it has to follow that, because how many rows are here? So there are m rows, right? So that means C times, so C times m equal to D into n, right? Because this each column has a D sum and there are n columns, so this condition has to be satisfied, okay, very good. Now we have to prove that, Qm times X times Qn equal to X, okay. So let us open it. So Qm was 2 by m jm minus im, okay, and then X times this, so maybe I can directly write here, so 2 by n, then X times jn, okay, x times jn, and then another term is nothing but x, right? Because this is, yeah, very good. Very, very good. So now till now our job is very, very easy. Okay, so x times jn, very good. Now what will be this quantity? If you see here, 2 by m jm minus im, okay, then x times jn is what? X time, if you see that, so there are n columns here, n columns here, and if you pick any row, how much, what is the sum of the entries? This is equal to c, right? So this is nothing but 2 by n c times j, and what will be this, so the dimension of this is m cross n, so this will be m cross n here, right, times the same matrix X. Okay, very good. So now maybe something more here. Okay, so this 4 by mn, then jm times c. So what can we write here? So this will be c. Now jm is getting multiplied with again jm, so m entries are there, so this will be m, very good, and then it will be multiplied by j m cross n. Okay, so now this term is done. Now what will be this term? This term will be 2 by m, right? Now jn is getting multiplied by this, right? So now there are d, so sum is here d, so this will be nothing but d by this m j. Now this is m cross n, right? So this is m cross n, very good. Now again I think this is same, 2 by n c j m cross n, very good, and then this is plus x. Okay, now if you see that, let us cancellation sum. So this is this 4 by n times c, so this is j m cross n. Okay, now can we make some what? Okay, so if you see, maybe we can now use the identity other we have just written earlier, 2 by n c j m cross n plus x. If you see from here, so cm equal to dn, so that means okay, so c by n, yeah, c by n equal to m by so that implies that c by n equal to d by m, right? Very good. So now we can make use of this. So these two conditions, so if we, yeah, correct, so these two guys are essentially the same, d by m and 2 by so c by n, so these guys are nothing but same. So this condition, so everything here will be vanishing, so it is 0, it will give you equal to x. Very good. Now the third condition is this: we have to prove that q2m x equal to smaller j, rather, sorry, smaller, or maybe just all one. Okay, all one vector of 2m minus x here. Okay, so actually I have to write here, so let me write, it's not jm, rather it should be all one. Okay, 2m. Okay, very good, sorry about that. Yeah, very good. So I mean, how can we prove that? So we know that, so let me write it here. So this is nothing but 2 by 2m, then j 2m, right, and then j2m, and then what, there was I 2m. If we subtract, if we multiply, sorry, with x here, okay, so what will happen here? So this will be, okay, 1 by m, j2m into x, right? In x there are exactly one m number of ones, right? So this will be nothing but m times again a vector which is all one vector, right? Okay, this will be give you this vector, well, this will be this, and then, oh, very good, so now we are removing minus x here, right? Oh, this is correct. Oh, done. 2m minus x. Basically, whenever there were ones, now it will convert to 0, and whenever there were 0, it will be converted to 1. Very good. Okay, now how can we make use of this fact, right? So I have kind of written this matrix Q in some special form. How can we make use of this? How can we make use of this? This is an orthogonal matrix. Okay, now let us try to make use of this. Okay, now if you see that, if you see our matrices, or maybe G and now G transpose, okay, how can we write the adjacency matrix of G? Remember, G was in some structure, right? There were blocks, not blocks, there were some subset of vertices, and there were a special vertex that we call Y, right? And they were satisfying some property, okay? Now let us write down the adjacency matrix of this. So adjacency matrix of G can be actually written as in some block forms like this. Okay, so there were k blocks, and then there was block. Now we will write the blocks in terms of the subsets we have seen in the picture, right? So, and there were k of these, and then there was a special what we call subset we call Y. Okay, so the adjacency matrix will look like this: A1k, then sorry, A1n1, A12 up to A1k, and then there was this, right? So this is corresponding to, suppose, the first subset, and similarly you can write it A21, or maybe the transpose of this, because this matrix has to be symmetric, A22, okay, A2k, okay, and then AY2, and so on up to here. So let me here write similarly maybe k1, then AK2 here, okay, and then AKK here, AKK and AYK, okay, and here it will be like this. So suppose let me make it bigger, okay, so this one, and now here it will be actually, let me write the transpose of this one, AY2 transpose, and this will be some, and this will be some A, this will be some AY. Okay, very good. So now you see that before moving ahead with the proof, you see that if you see these chunks, okay, so let me see this one. You pick any Aij here, okay, this is a block. This is a block where every row has the same sum, right? And every column also has the same sum. This is nothing but, it tells, Aij tells what? Basically these are the nothing but the adjacencies of, adjacency basically neighbor of basically xi to neighbor to xj, and vice versa, right? And by the rule that every vertex will have the same number of vertices in any xj, okay, so here you will see that every Aij has constant row sum and constant column sum, okay. Other observation is this: if you pick any, so suppose you pick any AYI here, any AY, or I mean, yeah, maybe you take anything, okay. Every column of this matrix, every column of this matrix will have either all the column, whole column is filled with 1, or there is no one, or there are half number of ones, okay. Rest of the half entries are 0, okay. Now immediately we see that we can make use of Q, the orthogonal matrix we have just formed here, and then we can multiply that Q with right hand side and left hand side to give this beautiful matrix, okay. So what is this? So you can actually cook this matrix. If you can cook this matrix, suppose this is Qn1, Qn2 up to Qnk, and then there is identity matrix with the size of mod y, okay. So this Ni is actually, you can assume that the size of xi, okay. Now you multiply this bigger matrix, and these are rest of the places 0, okay. What will happen? So if you multiply Q times Aj times Q, you will be getting A of G tilde. Why it is so? Because if you multiply this Aij will be multiplied with Qi, Qni, and then on the right hand side Qnij, but since these are constant row and constant column sum, so this will be equal to same, right? The matrix will not be changing because this will be giving you x, nothing will be changing, okay. And but if you multiply and this by this matrix, okay, when q and I is multiplying with any AYI, okay, so whenever in any column when there were half the entries were equal to ones, these half entry will be equal to 0 and rest of the half entry will become 1, okay. So this is nothing but switching, right? The switching that given by Godsil and McKay, right? So it says that any vertex in Y, if it is connected to suppose half of the vertices in any of x1 to up to xk, remove those half, okay, and instead connect to rest of the half vertices of that particular xi, okay. So this is actually this operation will give you that switching, and then what? And then we are done. This guy will be multiplied both and side by, but basically this will not be changing because this is multiplied with I on right hand side and I on the left hand side. This will be again. So rest of the connections are intact, only the switching part is there, okay. So very good, and with this we have indeed proven that these two guys have, so G and G tilde will have the same eigenvalues, okay. Very good, okay. By the way, it is not guaranteed that this will always lead to cospectral graphs. Basically G and G dash may be isomorphic. For example, if you take suppose this graph, okay, suppose you take this graph, okay, and take this vertex, okay, this vertex, suppose you treat this as y and this as x, just there is one vertex, okay. Now you see that every condition is following, right? So every if you talk about the block matrix here, so every column, row and column sum is same here because this is a regular graph, and suppose this is connected to these three vertices, okay. After GM switching, okay, what will be the your graph? So let me number them: 1 2 3 4 5 6. So this will be this, right? So 1 2 3, now they will be connected to 4 5 6, right? So 6 5 and 4, so this will be your, suppose this is called V vertex, so V, okay. But still if you see that these two guys are isomorphic, these two will have the same eigenvalues. In any case, if the graphs are isomorphic, so they will have the same eigenvalues, okay, but not vice versa. So in the next lecture we will see some beautiful examples where this indeed can give cospectral graph. That means the graphs are non-isomorphic, but due to this construction these will have the same eigenvalues, okay. So till then, thank you very much and see you in the next lecture.